Hello everyone, and welcome back to this course on BSP 303, that is Digital Systems and Applications. So this is the lecture number 2 on BSP 303. So if you remember, in lecture number 1, we have discussed the introduction to digital circuits, and also we have discussed the characteristics of various number systems. So in this lecture, we will try to see how we can do the conversion from one number system in another number system. For example, first we will try to learn how we can do the conversion from binary to decimal number system, and then again we will see the conversion from a decimal to binary number system. Also, we'll try to see one different methods in doing so, that is the double date method. And then similarly, we will try to see the conversions of other number systems into binary and vice versa. So let us begin our discussion, and let me share the screen first. So, okay, so here we go. These are today's content. As you can see here, that the lecture number 2, we are going to study about the conversion of the number system. Okay, so let me just slide this a little bit down. Okay, so let us first begin the conversion from the first one. Let us begin doing the conversion from binary to decimal number system. I mean, how we can do the conversion from binary to a decimal number system. For example, we will start with some of, I will try to cover some of the example. Example number 1, suppose, let us say I have this number system here. Suppose I have this number system 1, 1, 1, 1, and 1. Okay, I need to convert this number system into a decimal number system that is having the base 10. Okay, so the process is not quite simple. So let me try to write down the steps here, starting from this writing the binary number system first. So now you know that there are the weight are assigned to this. We'll just, what we will do, we will multiply every digit by their respective weight assigned. Okay, so here what is the weight assigned to this left, I mean the rightmost? This is 2 to the power 0. Similarly here it is 2 to the power 1. Then we have 2 to the power 2. Then we have 2 to the power 3, and then we have 2 to the power 4. Okay, we just need to multiply these with their respective weight assigned, and then keep on adding these numbers, and then we will get the decimal equivalent of this particular binary number. So let me show you here. Let me start writing from this. The MSD is 1, so we have 1 into 2 to the power 4 plus the next one. Now we have done this. Now the next one, this is also 1, so this is 1 into 2 to the power 3 plus, we'll start with this one. This is also 1, so this is 1 into 2 to the power 2 plus, then this one, this is also 1 into 2 to the power 1 plus, then the rightmost one, that is 1 into 2 to the power 0. Okay, so here we have, all right, so 1 into 2 to the power 4. Now if you just multiply this 2 to the power 4 into 1, you will get 16 plus, this is 8 plus, here you have 2 to the power 2, that is 4. 4 into 1 is 4 plus, you have 2 plus 2 raised to the power 0 is 1, and 1 into 1 is 1. Okay, so what do we get here? If you plus all these, I mean 8 plus 4 is 12, 13, 14, 15, 15 and 16, that is 31. So we have this 31 to the base 10. All right. So this is how you are going to convert one number system into another. Suppose you have a decimal number system also. So what do? You can take another example of how to do the conversion. You will suppose I have any number. Let me say that I have the next example. Let me write it in this way. Suppose let me try to write a very simple number here, 101.10. Okay. Now this number I need to convert it into the respective decimal number. What will be the conversion into? Now there is a radix point also here. So now what is the weight assigned after the radix point? Suppose this one. The weight, we'll just need to keep on multiplying the digit by the weight assigned and keep on adding all this. Okay. So you can see after the radix point, the first digit is 1. So you will just multiply 1 this to the respective weight assigned, that is 2 to the power minus 1. This would be 2 to the power minus 2. Okay. So let me just put it down here. So first is this 1. So I will just write this is 2 to the power 0, 1, and 2. Okay. So 1 into 2 to the power 2 plus the next digit is 1, that is, sorry, 0. 0 into 2 to the power 1 plus you have 1 into 2 to the power 0 plus. Now after the radix point you have the first one is 1. So this would be, I mean, 1 into 2 to the power minus 1. Okay. Plus then you have 0 into 2 to the power minus 2. All right. So now 1 into 2 to the power 2, that is 4. Okay, 4 into 1 is 4 plus 0 into 2 to the power 1, you will get a 0 plus 1 into 2 to the power 0. Now 2 to the power 0 is 1. Okay, 1 into 1 is 1 plus what do you have? 1 by 2 to the power 1 by 2 to the power 1. Okay, 2 to the power 1 is 2. So this is just 1 by 2 plus you have 0 into something, you will get a 0. Okay, so fine. 4, 5. You have this side you have 5 plus then what do you have? 5 plus 1 by 2. Now what is this 1 by 2? 1 by 2 is nothing but it is 0.5. Okay. Now if you add these two, what would you get? You would get 5.5. Okay. So the decimal equivalent is 5.5 to the base 10. Okay. So this is how you are going to do the conversion from binary into decimal. Now let us go and see the conversion of decimal to binary. Okay. So the next one, the second one, that is we will call this as the decimal to binary. Decimal to binary conversion. Okay. Okay, we'll again keep the, I mean, suppose you need to convert these 13 to the base 2, 13 to the base 10 to the equivalent binary. We do not know that binary, so I'm just writing something. A vacant space here, then to the base 2. So now in case of binary to decimal, you have multiplied by the weight assigned. Now what will you do here? You will just multiply it by the base of the, you will just divide this number by the base 2 and keep on noting down the quotient. Okay, so let us see how we can do that. Suppose I have this decimal number 13. I will keep on dividing this 13 by 2 and note down the quotient. 13. Okay, here I have the quotient and note down the remainder. We need to note down the remainder, not the quotient. Okay, so for that, so 2 into 6, you have 12. Then what is remainder? 1. Then again this 6 will come down here. Okay, you will keep on dividing this by 2. Then what would you get here? 2 divided by, okay, quotient you will get 3. Then you will get a remainder as 0. Now again this 3 will come down here. Okay, 3 divided by 2. 3 divided by 2, 2, 1 is 2. Okay, and then 1 is the remainder. Okay, then what do you have here? 1 divided by 2. Now this 1 divided by 2, it is actually 0 because you cannot divide 1 by 2. So the remainder is 1. Okay, that's it. So we are done now. This is the last step. Now you will have to note down the remainder. You can see in Q and R, in this R you see, let me just draw an arrow, an upward arrow like this. You will have to start counting this number from the bottom to top. Okay, so the equivalent of 13 is nothing but it is 1101. Okay, so here on this gap I'm just going to fill out 1101. so this is how you are going to do the conversion. Okay, so now specifically let me tell you how you can do the conversion of a fractional part. So here we have seen only the conversion of the integer part. So now I will tell you the conversion of the fractional part. Okay, so let me go to the next one. For example number 2 in this particular case. So let us say I have this number 0.65625. 65625. So I need to convert this decimal number into particular binary number. So this binary number will also be in decimal. This is just the fractional part I am taking. I am assuming that there are no integers, only the fractional parts. Okay. So what would you do for the fractional part? You will just multiply continuously with by 2. Okay, so 0.65625 into 2. In the integer part, you have divided by 2 the number. In the fractional, for the fractional part, you will do the multiplication of the number. Okay, and note down the integers which are generated. Here, whatever integers are generated in the result, you will note down only that one. Okay, so if you do this multiplication, your answer would be 1.3125. 3125. Now in this case, what I will do, I will note down the integers. Now what is the integers in this case? This is 1. Just focus on this one. Okay, now again the second step, the fractional part you will take, that is, you see the fractional part here, this is 0.3125. Okay, so let me take this 0.3125 into 2. Okay, so now you multiply this by 2, you will get 0.625. 0.625. Okay, and again you please take this fractional part, that is 0.625. 0.625 into 2. Okay, so what would you get? You will get 1.25. 1.25. Now you again take this fractional part, that is 0.25. So that is 0.25 into 2. Okay, so you will get 0.5. Now you take this 0.5 again, so that is 0.5 into 2. You just multiply this, so you will get 1.0. Now the step ends here because you go get in the fractional part you get a 0 here. Okay, now you just note down these integers which are generated. You please see these integers and you now go from up to the bottom side. Okay, so therefore what number you get? You get this as 0.65625 is nothing but it is 0.10101. Okay, so here I will just write this as 0. Starting from top, 10101. So it is 10101. So in this way, now if you are provided with any a mixed number, that is, which is having the integers part as well as the fractional part, then you should be able to do this conversion. Okay, so you can try out with different examples in this case. Okay, so let us move to the next section of today's lecture. That is, we have seen just the one conversion now. Now another important method is there, a shortcut method, and this shortcut method is only useful for binary integers, not the fractional part. Okay, just for the binary integers. Suppose you have a very long binary integers, then it is most appropriate to use this method here. Okay, if you have a long string of binary numbers, then this method is very useful. This method is actually known as the double dead method. Double dead method. Okay, and as I told you that I mean this method is useful for a only binary integers. Okay, so let me just write down here, these are only just for binary integers. not the fractional part. All right. And if you have a long string of binary, or you can say if the binary number is very large, these are useful for large binary integers only. Okay. So see, what are the steps? The steps are, you need to first double the first bit. Whatever first bit is there, you need to double it, which is on the extreme left. Okay. And then add this double value. You need to add the double value to the next bit on the right. Okay. And the second step is that double the sum obtained and then add the double value to the next bit. And you need to continue these steps. Okay. So it may be pretty difficult to follow, as I say, but let us take one example, then everything will be clear. Okay. So for example, the question is, we need to convert this particular number 1110001. So I need to convert these to decimal. I need to convert these to decimal using this double dead method. Okay. So the first step number 1 is double the first bit. You see that this is the first bit which I have, that is 1. Okay. So I just need to double this bit. That means 2 into 1. I'm doubling the bit. So 2 into 1 is equal to 2. And then you need to add this double bit to the next one. Okay. Now I'm adding this double 2 plus to the next one. This is the next one, 1. Okay. So 2 plus 1, you have this as 3. Okay. And now again, you will keep on following this step. Okay. Now in the second step, you will take this 3. Okay. And double this. So second step, you need to again double 2 into this 3. Okay. 2 into 3, you will get 6. Okay. And then you will add the 6 to this 0. Okay. The next step is you will add this 6 to 0. 6 plus 0 is 6. So again, in the third step, you will continue this. I have a 6 here. I will double this 6. So 2 into 6, that is nothing but that is 12. And then I will have to add this 12 to the next bit. And what is the next bit now? That is 0. Okay. So 12 plus 0, I got the number as 12. Okay. So let me just slide it down. All right. Now the fourth step, that is, I have 12 here. I will just double this 12. So 2 into 12. Okay, 2 into 12. Then you have this 24. Then you will add this 24 to the next bit. You see 24 plus, what is our next bit? You can see here, this is 1. Now you have to stop it. Okay. So 24 plus 1, you have this 25. So the decimal equivalent of 11001 is nothing but it is 25. So here now I can write here as it is 25 to the base. So this is known as double dead method of conversion. And remember that this method is applicable to integers only. And in case you have a large integers, like you have a large string of integers, then this method may be very easy. I mean, easier than the earlier method which we have. Okay. So you can, similarly in this case also, you can, I mean, try out with different, I mean, number system. Okay, with different examples. I mean, so before I conclude, I mean, today's section. So let me first tell you another important point. We are still on binary to decimal and decimal to binary conversion. Okay, and then before we go to the next conversion type, I will tell you one important topic here, that is the sign magnitude representation. Okay, so I'm just writing here sign magnitude representation. This is quite interesting here. So digital, you know that as I mentioned, that a digital circuit can understand only discrete signals. That is, I can say that the digital circuit can understand only zeros and ones. Okay, these are the values which the digital circuits can understand. Okay, so therefore, what do we need? We must use the same symbols we also have to use these same symbols to indicate the sign of the number. You know that in number, see now, the number, the particular number which we may be talking about, that may be a positive number or a negative number. So since the digital circuits can understand only 0 and 1, so you need the same digit 0 or 1 to represent the sign of the to also represent the sign of the number. Okay, and normally an additional bit is actually used. If you want to write the sign of that particular number, you have to use an additional bit as the sign bit. Okay, this additional bit you have to use as the sign bit to represent the number. Okay, so this will represent different sign. An extra bit would be represented. We use the sign bit, and it is placed at the most significant bit. So this is actually placed at the most significant bit, MSD. Okay, if any number is given to you and then it is asked to you that what is the sign of this number, then you need to see the MSD of the number. Okay, usually the sign bit is placed at the MSD. Okay, most significant bit, most significant digit. At that place it is, there's this sign bit. Okay, so let us see the example. I think it will be clear if we see the example. Okay, now what is the number? For example, I say that I have this number. Okay, now since two numbers are used to represent the sign, a 0 is actually used to represent a positive number. Okay, and then a 1 is actually used to represent a negative number. So for example, let me take this number 0 1 0 0 0 0 0 0 0 1 0 0 0, then I have 1 0 0. Now I have to, let us say for example, I have to represent this number as the sign magnitude. I have to represent this in sign magnitude representation. Okay, so as I told you that in sign magnitude, the MSD, you have to see the MSD. Let me use different color here. Please see this MSD now. This one, this is the MSD, this is a 0. So this corresponds that it is a positive number. Okay, now this will represent the sign and the rest will represent the magnitude. The other digit, this digit will represent the magnitude. Okay, the blue will represent the magnitude. Now what is the decimal equivalent of this one? You apply the same technique which we have applied, just keep on multiplying this with their respective weight assigned. So you will find that the magnitude of this blue the number which is on this blue box is actually 68. Okay, इसका magnitude क्या होगा? 68 होगा. You guys can just check it, the magnitude. So ultimately what would I write now? I would write that this 0 1 0 0 0 1 0 0 is nothing but it is plus 68. Okay, if you have a 1 here, it would be minus 68. So this is how you would represent in sign magnitude representation one particular number. Okay, so this is about the sign magnitude representation. Now see, we have different other type of conversion as well, but before that, before I actually go to the other type of conversion, let me first tell you one important topic here again, that is the the BCD here. Now before I conclude, I will tell you about this BCD. What is this BCD? This is binary coded decimal. Okay, so what happened, it is also known as, this binary coded decimal is also known as 8421 code. Okay, why 8421? It will be clear to you. So in a while, every decimal, for example, every decimal number, this side I am writing the decimal 0 1 2 3 4 5 6 7 8, and then it is 9. Okay, so every decimal, it is represented by a 4-bit binary numbers. Okay, it is represented by a 4-bit binary, and that 4-bit representation is actually known as binary coded decimals. Okay, so why it is 8421 code? So if you have to write down all these numbers, 0 you will write down in 4-digit information, that is 0000, and 1 you will write as 001. 0001. Similarly, 2 it is 0010. Okay, so now here it is 8421 code. We'll just start writing from 8 zeros first. And then again 8 1. So up to 9 only we have the decimal number. So we'll write only up to this 8 and 9. Okay. Similarly, here now you have 4. Now you have to start writing 4 zeros. 1, 2, 3, 4, and 4 ones. 1, 2, 3, 4, and again 4 zeros. Up to 2 0 only we can write here. Now 2 0 and 2 ones. 2 0 and 2 ones. Again you have 2 zeros and then 2 ones, and again 2 zeros, and alternate 0 and 1. So you have 0 1 0 1 0 1 0 1 0 1. So here you see this side is actually our BCD representation. Okay, and this is also known as 8421 code. Now, for example, if you have to represent this in BCD, so suppose the question is to represent this in BCD binary coded, how would you represent? You would represent 2 as 0010. So this 2 it is 0010, and then you would represent 6 as 0110, and this 6 as 0110. So this is your 26 in binary BCD form. Okay. All right. So this is how you will write down the BCD, and it is also known as the 8421. So with this, I would like to stop this second lecture here. And, so we have come to the end of this lecture number 2. So in the next upcoming lecture, we will try to see other type of conversion, like from binary to octal, and then octal to binary, binary to hexadecimal, hexadecimal to binary, and all those different such examples and different such kind of conversion we'll try to see in the next lecture. So thank you everyone, and see you all in the next lecture number 3. Thank you.